Welcome to another chapter of Nefertiti project. So this is José Ignacio Lozano from the Technological Center Funditec, and I'm currently working as a principal researcher in the field of advanced material and processing technologies. Today, we are going to talk about the different anchoring techniques of a chemical catalyst and how they can be modulated depending on the nature of the catalyst and the substrate on which it will be supported. In this chapter of the course, we will see different aspects of the anchoring technique, such as why anchoring catalysts on substrates, the advantages and disadvantages, or even limitations, the need of a substrate preparation and the methods involved, typical anchoring elements and their functionalities. We will talk about catalyst deposition, the different methods for the coating step, the chemical physical characterization of achieved surfaces, techniques and some typical values of each one. Anchoring techniques also will be explained in 3 use cases, namely for organic catalysts, for organometallic catalysts, and also for inorganic catalysts. Finally, conclusion section will summarize the most important tips in the field. Before moving to the specific of this presentation, it could be good to revise some basic concepts of this topic. Anchoring is the process through which a catalyst or a mixture of catalysts is deposited and fixed on the substrate. Anchoring provides important advantages in the heterogeneous catalysis area, such as promoting a better dispersion and orientation of reaction centers, allowing to construct complex catalytic surfaces by combination of several layers, allowing to immobilize the catalyst in continuous flow reactor. Anchor catalysts should present similar or even high catalytic activity respect to the catalyst itself. In terms of reproducibility, repeatability, selectivity, and yield. As the catalyst and the substrate have different composition, properties, and shape, it's necessary to use a combination of physical and chemical techniques to make them compatible. First, let's start with the substrate. Immobilization of a catalyst is usually carried out on metal supports in reactor through which the phase containing the reagent circulates. In the case of microreactors, catalyst immobilization will depend on the type of microchannel achieved in the surface, which can be anisotropic, partially anisotropic, or even isotropic. Achieving one or another will depend on the fabrication method, for instance, micromachining, lithography, or etching. The dimensional shape of the microchannel can condition the amount of catalyst deposited, its stability, and the final catalytic efficiency. Prior to catalyst deposition, the channels must be cleaned and activated. 2 main methods can be used: chemical cleaning with hydrofluoric acid or piranha solution, or physicochemical cleaning, for instance, the use of plasma activation. All of these methods produce an activated surface containing hydroxyl groups that later on will be used to anchor the catalyst. The process can be done directly or through immediate molecules called anchoring elements. In order to fix the catalyst to the surface of the support, different anchoring elements can be used, being the most common ones the silanes. These chemical compounds contain a double functionality. At one end, a silicon alkoxide with 3 alkoxide groups that react with the hydroxyl groups of the surface. At the other end, a second functional groups like amino or epoxy, which will react with the functional group in the catalyst. Of special mention is the use of cyclic athasylanes, which by ring opening and hydrolysis provide strong, durable anchors, and which is most importantly, with optical characteristics. They provide high transparent interlayers without causing interference into the passage of light, which make them very useful in the deposition of catalysts that work in photocatalytic process. There are several methods to deposit the catalyst and the anchoring element on the surface. In the deep coating method, the substrate is immersed at a certain speed in a bath containing the compound to be fixed. Once out of the bath, the solvent is removed, leaving a very thin layer containing the catalyst on the surface. In the spin coating method, a drop of the coating solution is applied on the surface, which is rotating at high speed. The centrifugal forces distribute the solution over the entire surface, and Evaporation of the solvent provides an homogeneous surface in both area and thickness. The layer obtained by these two methods give surfaces with a thickness of less than 50 nanometers. To achieve thinner layers, atomic and molecular layer deposition should be used. This technology consists of the deposition of a layer by creating a mist containing either atoms or molecules that are deposited on the surface. In this case, the obtained layers have thickness in the range of 5 nanometers. After application, most of the samples require a drying step or thermal curing. The characterization of the achieved film can be done by water contact angle technique. Normally, when no film is deposited on the activity surface, the water contact angle is near 30 degrees or even less, indicating a hydrophilic character of the surface due to the high concentration of the hydroxyl groups. As soon as silver film is deposited and attached to the surface, the contact angle rises, indicating an increment of the hydrophobic character of that surface. If a second layer of a new chemical is deposited and react with the first layer, the water contact angle value will change again. It is interesting to mention that the same anchoring group attached to different functional groups in the catalyst can produce film with different water contact angle. In this example, it's easy to see the differences between glutaraldehyde, pyrrole, and phenanthroline branches. This technique can be seen clearly in the following picture. This technique consists of application of a micro drop of water on the surface to be tested and measuring the angle formed between the activated surface and the external profile of the drop. The higher the angle, the lower the hydrophilicity. In this example, it's easy to see, and in a direct way, to control the deposition of the different layers that can form a catalytic surface arranged on a substrate. The monitoring of layer formation and characterization can be followed by another techniques like infrared spectroscopy, refractive index, or layer density per unit area, as it can be possible to see in the slide. Now, we will revise some use cases to see the practical application of the anchoring techniques. Let's start with organic catalyst. One of the most interesting situations is the creation of complex structure on inert substrates by means of layer by layer technique. In this example, a polyethylene surface can be activated by means of plasma treatment, creating hydroxyl groups. They cannot react directly with the catalyst and make it necessary to use an anchoring element. The selection of this molecule will be made according to the functional groups present in the catalyst structure. For example, aldehydes, acids, amines, hydroxyl groups, etc. So the hydroxyl groups created on the activated surface react with an end of the anchoring element, leaving the other end of this element oriented towards the outside of the surface. In a second step, these active ends react with a functional group in the catalyst, creating in this way the first layer of catalytic organic catalyst. Next, onto this layer, it's possible to keep anchoring successive layers using the same mechanism, building the system from the surface towards and leaving the organic catalyst fixed in a multi-layer structure. In the case of organometallic catalysts, anchoring process can be done by two ways. First, by covalent bonding between the ligand belonging to the metal coordination sphere and the group acting as an anchor, is the example on the right, or through the metal center by using a vacant coordination site in the metal, which will always be additive bond between the molecule acting as anchor and the metal, the left example. The difference between these two types of anchoring is the strength on the bond achieved, being the latter more labile than the former. As rule of thumb, stronger covalent bonds should be preferred. However, this is not always possible, and anchoring has to be undertaken by simple coordination in vacant position of the metals. The case of the position and anchoring of catalysts of inorganic nature present some particularities. Their chemical characteristics, they usually are oxides, and the low dispersibility properties make them hard to be dissolved or suspended. The lack of reactive points in that metal oxide make them impossible to be immobilized by means of the already mentioned anchoring molecules that use surface functional group to get fixed. The way to anchor the catalyst on the substrate is often by simple dispersion of the oxide that make up the catalyst in the hollows, pores, channels, and surface of the substrate on which it is deposited. There are several methods to deposit this type of catalyst: the use of colloidal suspension of catalyst precursors, the dispersion of a catalyst on titanium oxide solution and further deposition, the use of photochemical process as a tool to increase dispersion, or the use of binders as a way to modify the substrate surface. Sometimes, due to the incompatibility between the catalyst and the original substrate, it's necessary to insert intermediate molecules or structure that act as a dispersion system of the catalyst. Examples of this type of structural molecules are resins, titanium organometallics, titanium silicon complexes, or carbon nanotubes. One of the strategies consists of anchoring titanium organometallics derivatives. One anchor and calcine produced titanium oxide surface modification use a substrate on which to disperse the catalyst. This is the example on the left. The same can be combined with mixed titanium and silicon complex, the example on the right. By means of hydrolysis reaction and subsequent condensation, the complex produce the formation of a mixed structure of silicon and titanium, and possibilitating the formation of substrates that can be used for the dispersion of the catalyst of inorganic nature. Another strategy of inorganic catalyst immobilization is the use of carbon nanotubes. The use of carbon nanotubes as supports for catalysts is of special interest where high electronic conductivity is required. However, one of the disadvantages of the carbon nanotubes is their poor dispersibility, as they tend to aggregate, preventing the formation of homogeneous catalytic surfaces. To overcome this poor dispersibility, polysilyl sesquioxane structures are commonly used. They are bound to the carbon nanotubes to increase dispersibility and anchoring properties to the substrate. The anchor of the post to the carbon nanotubes occurs through the acidic groups generated in the carbon nanotubes. These posts can be attached to the carbon nanotubes through direct covalent bonds between the two structures. Catalysts are introduced by using their precursor, such as metal nitrates, and transforming them into the corresponding oxides by calcination. We can finish this chapter with some conclusion remarks. Anchoring of a catalyst on a substrate presents important advantages in heterogeneous catalysis, especially in continuous flow reactor applications. As the catalysts and substrates have different chemical composition, properties, and shape, it is necessary to use a combination of physical and chemical techniques to make them compatible. To help fixing the catalyst to the surface of the supports, bifunctional anchoring elements can be used, being designated the most common ones. Substrate surface must be prepared and activated prior to catalyst deposition, creating hydroxyl groups that later on will be used to immobilize the catalyst. Both anchoring element and catalyst can be deposited on the substrate by similar method, being the most used deep coating, spin coating, or molecular layer deposition. There are some peculiarities in the selection of the anchoring technique depending on the nature of the catalyst. Covalent bonding should be prioritized whenever possible. I hope this chapter will be useful for your formation, and thank you for your attention.